Assalamualaikum dear students. Today we start a new topic of quantum mechanics 1, operators. What is an operator and how to represent and how to write operators in quantum mechanics. And the types of operators, in which two types of operators we discuss in this lecture is linear operator and non-linear operators. Related examples and questions solved in this lecture. Of our lecture, firstly we discuss about the operators, what is an operator and example of the operators, and then how to represent and how to write an operator in quantum mechanics. After that, the types of linear operator. Firstly we discuss about the linear operator and the products of the operators, examples of operators and example of linear operators. Two conditions of linear operators which satisfied this operator is a linear or non-linear. So after that we define non-linear operator, which is the opposite of the linear operators. If any operator is not satisfied any condition of the operators, linear operator, then this is non-linear operator. So after the example we solve whether this operator is linear or non-linear. So in the last student activities, related example to solve all the students, and the last one is reference books. Students, today topic is operators. Operators is most important in quantum mechanics. Without operators we cannot solve the numericals or problems of quantum mechanics. So firstly we discuss about simply the definition of operators. The simple meaning of operators is that an operator is a symbol that tells the compiler to perform specific mathematical or logical function. This is the simple definition of operators. So the definition of operators in quantum mechanics is slightly different. So in quantum mechanics, students, we know that every particles have associated with a wave. So what is the position of that particles and what is the momentum of that particles and time which move particles having associated with wave. So all these terms, for the measurements of all these terms we use operators. So we can say that all possible measurements we can make on a particles is described by operators. So students, if we apply operators of any function, then we can get a new function, or simply we say that we apply the operators on a wave function and get information. So if we apply an operator on a wave function, then we can get a new wave function. So the definition of wave operators in quantum mechanics is that an operator A, and students, we represent the operators with alphabets, and in the alphabets upper head cap. This is the representation of operator in quantum mechanics. If we put a cap on the alphabetic A, B, C and so on, and this represents the operators. An operator A is a mathematical rule that when applied to a ket vector, or simply we say state vector of psi, which transforms it into an other ket. It means that if we apply operator on the wave function or a ket function, ket vector, then it's changed into an other ket vector or give an other wave function. So this is the ket vector of psi. Transform it into an other ket which is psi dash. If we apply operator, then change the state of the ket vector of psi. So of the same space, It means psi dash and psi cat having the same space, belongings to a same space. And when it acts on a bra or a state vector of phi, transform it into an other bra or a state vector of phi dash. It means also change the state vector of phi. It means also change the cat vector into another cat vector and phi vector into an other phi dash vector. It means cat vector and bra vector also change when we apply an operator on that state vectors. It means that A is an operator which apply on a cat vector psi, which is equal to the psi dash of cat vector. So this is about the operators. Representation of operators. No students, in the previous type we define operators, what is an operator, and simple way how to represent an operator. But the complete description of representation of operator is here in these slides. An operator is symbolically represented by an alphabetic letter, Greek or Latin, with a hat on the top of it, with or without a subscript or superscripts. It means that if simply we have an alphabetic letter and put a hat or a cap on the top of it, then it represents the operators. Here is X, and if we put a cap on the X, then this represents the position operators, because in quantum mechanics for the representation of position we use X alphabetic letters. So if we put a hat on the top of it, then it represents the position operator without subscript or superscript. If we put a subscript, then it also represents a operator. P of X, it is the momentum operator, and this is the momentum operators in the direction of the x-axis or the horizontal direction. So if we put a y, P of Y, then represents the momentum operator in the direction of the y-axis. And also we use P of Z in the direction of the z direction. In three-dimensional system, we represent the momentum operators by P of X, P of Y, and P of Z. So if we simply write P and the hat on the top of it, then we can say that this is the momentum operator. So this is the representation of momentum operators, and we can also use small letters and some mathematical terms for the representation of operators, like A, capital A, and the hat on the top of it, it represents an operator A, and small a and the hat on the top of it, this also represents the operator, and alpha, beta, gamma also represents an operator if we put a hat on the top of it, etc. Operator is a mathematical tool that is always left side of the state function psi. Students, it is most important. Always operator means operate any function, operate any wave function, operate any state function, state vector. So we use an operator. So it means that an operator always put on the left sides of the function. Any function which is a state function, wave function, or state vectors, always put on the left sides of the function. If we put on the right sides of the function, then it's not means an operators, we operate this function. So always operate and measurements for the different quantities, different terms in quantum mechanics, we operate operator on the left sides of the function. So operator represents the momentum, energy, and so on, etc. and position. All operators must have eigenvalue and eigenfunctions. What is an eigenvalue and eigenfunction? Students, we know in the mathematics what is eigenvalues and eigenfunctions. Also in quantum mechanics. But in the next lecture we discuss about what is an eigenvalues and eigenfunction. Simply lambda and energy and Hamiltonian also use for the eigenvalues. We use lambda with the energy operators, and this is the eigenvalues, but we discuss completely in explanation in the next lectures. So this is the representation of operators. In the previous slide, students, we can see that an operator A we put on the left sides of the state vector or ket vector, then we operate. So always put in the sides. We cannot write operator A on the left side, right side. This is wrong, this is right. Now students, here is an examples of operators. We use different operators in quantum mechanics and physics. Here is linear momentum operator. We represent linear momentum operator with a P and hat on the top of it, which is equal to minus iota h cut del. And how to get minus iota h cut del? When we apply an operator on the momentum, then we get this equation. We solve this solution and we get the how to get momentum operator. We completely explain and solve these momentum operators in the next lecture. Gradient operators, which we represents by the del and the arrowhead, which is equal to the curly over curly x I plus curly over curly y j plus curly over curly z k, which we used in mechanics. Gradient operators, and gradient operators we represents the del and arrowhead on the del. Laplacian operator, which is equal to del square, which is equal to curly square over curly x square plus curly square over curly y square plus curly square over curly z square, which is also used in quantum in mechanics and also in mathematical methods of physics. Unity operator, which we use in quantum mechanics, which is equal to I, and it gives an ket unchanged because it is unity operator. When we multiply anything by the unity or by 1, no change on this function or any state function or wave function. So if we apply unity operator on the ket vectors, then ket vector is unchanged. These are the different operators we used in different courses of physics, and this is the examples of operators. Now students, products of operators and also say that properties of operators. The first property is products of two operators does not commute. It means that operator A and operator B, if we multiply operator A and operator B, which is not equal to operator B and operator A. If we change the order of these operators, then it is not equal both operators. So this is the commutation relation in mathematics also, and in quantum mechanics for the operators we can also use here. If we take two operators product which is not equal to the, if we change the order of the operators. So associative law with respect to multiplication holds. It means associative law in mathematics, we say that if we have three different terms and if we multiply first two terms and then third and also third and second and first inside of the brackets, this is the association law with respect to the multiplication. In operators or quantum mechanics, we operate three operators A, B and C. If we multiply operator A with B, then the product of operator A and B multiply with operator C, which is equal to the operator A and in the brackets in the bracket we multiply, firstly we multiply B and C, then the answer and the product of operator B, C with the operator A. No, student, one thing should be remember, order is not matter when if operator can be applied either on cat or bra. In other different properties, order is matter, and if we apply operator on the different state function or vectors, then always write on the left sides of the function. But in cat or bra vectors, if we apply operator, then order is not matter. Why? Here is a bra vector psi and operator A, and here is a cat vector of psi. This is the this term is specific term in quantum mechanics we used for further, and we say that the expectation values. That's why here is order is not matter. But in the state function or say wave function, the order of operator is matter, and we write operator on the left sides of the function. If we multiply operator A and B, the product of operator A, B with the state vector of or cat vector, which is equal to the operator A, and we multiply operator B on psi cat. Firstly operate B on the psi cat and then operate B, which is also equal both of you. If we multiply both operators, then apply on the cat vector, and if we apply the second operator on the cat vector, then apply on operator A, which is also equal. Students, and these properties should be remembered, and we use in different numericals and problems for solving. So that's why you learn and remember these properties. Now student, first type of operator is linear operator. Linear operator means the linear combination of the elements or function, wave functions. Then we operate, and how to equal these, what is the condition of the linear operator. So the definition of linear operator is that an operator A defined over a set of elements. Set of elements is said to be linear if it satisfies the given condition. Set of elements, students, you know that the set of elements is psi, phi, chi, and here is psi 1 and psi 2, the set of elements. And if we add these two elements, psi 1 and psi 2, and then apply operator A, then how to apply operator A on these elements, and separately we apply operator A on these elements. For example, we can write this term in this form: operator A into psi 1 plus operator A into psi of 2. So also another example of this linear operator is operator A. C is a constant, and we multiply constant with the state vector wave function psi, which is equal to constant is the, and operator A apply on the wave function, and we multiply the constant. It means that constants, so constant is outside of the brackets, and we apply operator not on the constant function, constant element, only apply on the wave function. So these are the two conditions of the linear operators. Now students, here is an example of linear operator. The question of this example is that to prove that P of x is momentum operator on the horizontal direction, in the horizontal direction, is linear operator. Let psi 1 and psi 2 be two elements of a vector space, and C is an arbitrary constant. So these terms are given, and we prove that momentum operator is a linear operator. So the first condition of linear operator is that if we have a momentum operator, this is a momentum operator which is multiplied with two different elements of a vector space, psi 1 plus psi 2. The condition is that we multiply this operator with this vector elements, both linear combination of these elements. So p of x into psi of 1 plus p of x into psi of 2. We prove this equation and take one side and which is equal to the other side, then prove the first condition. So students, we take the left hand sides of this equation. If we get the answer on the right hand side, then it's mean first condition is satisfied. So p of x is equal to minus iota h cut curly over curly x. Now students, I told you earlier, in quantum mechanics, the momentum operators which is equal to minus iota h cut, also discussed in the previous lecture, minus iota h cut curly over curly x only for the x direction or horizontally. If we take three-dimensional, then momentum p which is equal to delta minus iota h cut into del. We know that del is equal to curly over curly x plus curly over curly y plus curly over curly z. So here we take p of x, then we put and replace the momentum operator with minus iota h cut curly over curly x. So students, this momentum operator apply on the both elements of the vector space psi 1 and plus psi 2. So we multiply minus iota h cut curly over curly x into psi 1 plus minus iota h cut curly over curly x into psi of 2. So this is the momentum operator p of x into psi of 1. We replace again minus iota h cut curly over curly x with the p of x with plus p of x psi of 2. So this is equal to the right hand side of the equation, and very easy to prove the linear operator of momentum operator is a linear operator. So hence prove left hand side is equal to right hand side. The first condition of the linear operator is satisfied. Now स्टूडेंट सिंपल हमारे पास अगर कोई भी ऑपरेटर है उसको हम दो डिफरेंट वेव फंक्शन या वेक्टर एलिमेंट्स लेंगे स्पेस के, उसके साथ मल्टीप्लाई करें तो हमारे पास सेपरेटली उन दोनों के साथ मोमेंटम ऑपरेटर या कोई भी जो आप ऑपरेटर ले रहे हैं उसके साथ मल्टीप्लाई करें तो वो उसके इक्वल आना चाहिए। तो इस तरह से हमने लेफ्ट हैंड साइड ली, उसको मल्टीप्लाई किया, मोमेंटम ऑपरेटर को हमने रिप्लेस किया उसकी वैल्यू से, जो कि क्वांटम मैकेनिक्स में हमने इसको निकालते हैं, प्रूव करते हैं। जब हम इसको दोनों के साथ मल्टीप्लाई करेंगे तो ये 2 का कम्बिनेशन बन जाएगा हमारे पास। तो इसी तरह से फिर हम इसको रिप्लेस कर देंगे मोमेंटम की वैल्यू से, मोमेंटम ऑपरेटर की वैल्यू से, और इस तरह से ये राइट हैंड साइड्स के इक्वल आ जाएंगे। तो ये फर्स्ट कंडीशन ऑफ लीनियर ऑपरेटर जो है वो हम यहाँ पे सेटिस्फाइड कर देंगे। अब हम सेकेंड कंडीशन देखते हैं। Now the second condition of linear operator is that if we multiply a momentum operator with any vector element or a wave function with a constant, then which is equal to the constant outside of the momentum operator or operator, any operator, and multiply with the wave function or vector element. So we prove one side equal to the other side. So students, we take left hand sides momentum operator p of x into c into psi of 1. Now we put the momentum operator value minus iota h cut curly over curly x into c into psi of 1, which is equal to c. We know that c is a constant, so we take outside of the constant and multiply this into with the psi of 1. So minus iota h cut curly over curly x into psi of 1. So c, this value of momentum operator p of x into psi of 1. So left hand side equal to right hand side. Both conditions are satisfied. So momentum operator is a linear operator. Now students, इसमें भी simple कि आप अगर आपके पास कोई ऑपरेटर है और उसको ऑपरेटर को हम किसी भी एलिमेंट को कांस्टेंट के साथ मल्टीप्लाई करते हैं तो कांस्टेंट को हम बाहर आउटसाइड पे निकाल लेंगे, और मोमेंटम ऑपरेटर के साथ हमारे पास कोई भी स्टेट वेक्टर या स्टेट फंक्शन या फिर उसके साथ आप कह दें वेक्टर एलिमेंट आ जाएगा वेव फंक्शन। तो इस तरह से आपके पास ये कंडीशन आनी चाहिए। तो सिमिलरली यहाँ पे हमने लेफ्ट हैंड साइड ली और मोमेंटम की वैल्यू से रिप्लेस किया, c इंटू साई ऑफ 1 लिया। अब हमें पता है कि जब भी हम डेरिवेटिव लेते हैं किसी भी स्टेट फंक्शन का, किसी भी वेव फंक्शन का या किसी भी फंक्शन का, तो उसके साथ जो भी कांस्टेंट टर्म होती है उसको हम बाहर निकाल देते हैं। तो सिमिलरली जब हम इसका डेरिवेटिव लेंगे साई ऑफ 1 का तो हम कांस्टेंट को बाहर निकाल लेंगे। तो अब कांस्टेंट को बाहर निकाल लेंगे तो कर्ली ओवर कर्ली एक्स इंटू साई 1 का हम डेरिवेटिव लेंगे, ये भी आपके पास कांस्टेंट है, ये भी इधर आ जाएंगे आपके पास माइनस योटा एच कट। अब हम जानते हैं कि ये माइनस योटा एच कट कर्ली और कर्ली एक्स हमारे पास क्या है, मोमेंटम ऑपरेटर की वैल्यू। तो आप यहाँ पे लिखेंगे पी ऑफ एक्स बार इंटू साई ऑफ 1, वैसे आपके पास आ जाएगा और ये कांस्टेंट साथ में मल्टीप्लाई हो रहा है। तो यही हमारे पास सेकंड कंडीशन थी लीनियर ऑपरेटर की। तो सो लेफ्ट हैंड साइड इक्वल टू राइट हैंड साइड, बोथ कंडीशन सेटिस्फाइड, देन वी सेड दैट द मोमेंटम ऑपरेटर इज अ लीनियर ऑपरेटर। No, the other operator is non-linear operator. In the previous slide, we discussed about the linear operator and example of the linear operators. Now, students, what is a non-linear operator? Simply, if operator is not linear, then it means it is non-linear operator. So, the definition of non-linear operator is that if any one of the condition of the linear operator is not satisfied, then the operator is called non-linear operators. Students, you know that a linear operator has two conditions. The first one is if we multiply any linear operator with two different elements, addition of the two different vector elements or the state function or state vector, then equal to the operator multiplied by first vector element plus operator, then the second element separately equal to these elements. And the second condition is that if we multiply constant with the state vector or a vector element, then the product of constant and the vector elements multiplied with the operator, which is equal to the constant outside of the brackets and inside of the bracket, is operator multiplied by state vector or a vector element. So these are two conditions of linear operator. If one or any one of the condition is not satisfied, then we say that these are the non-linear operator, or an operator which is not linear is called non-linear operator. Both are the definitions of the non-linear operators. Here is an example of non-linear operator. The most important example of non-linear operator is a scaling operator. So we take an operator s of x and simply s which is equal to x square. So here is an operator and we take the square of the x and prove that this operator is a linear operator or a non-linear operator. To prove that square operator is non-linear operator, we will prove both conditions. So the first condition is that the square operator, and we take two function or state vector or vector elements, for example f plus g, two different functions f plus g, which is equal to the operator multiplied by the first function plus operator multiplied by the second function. So this is the left hand side and right hand side. Firstly we take left hand side, which is equal to the square into f plus g. So we apply square operator into f of x plus g of x. Simply write f and g, but here we prove x square, x del operator, s operator scaling operator is equal to x square. So we take f into x plus g of x. So this is the function. So we take the square according to the given question and given condition. So taking the square, and square is equal to the f of square of x plus g of square of x, plus we know that if we take the square of two vectors and two elements, then the square of the two elements. This is the formula of a plus b square. So students, we know that a plus b square is equal to the a square plus b square plus 2ab, which is equal to a square plus b square plus 2ab. So here a is f of x plus b is f g of x. So we write f square of x plus g square of x plus 2 f of x into g of x. This is the equation 1. So this is not equal to the right hand side. So we take right hand side and solve. Then we saw the both answer of these sides are equal or not. If not equal, then this square operator is non-linear operator. So the right hand side is equal to s of x plus s of g. So s f of x plus s g of x square operator. So f of x का square according to the given condition plus g of x का square. This is equation 2, but not equal equation 1 and 2. So for equation 1 and 2, we get that first condition is not satisfied. It means that the square operator is non-linear operator, not an linear operator. So now we prove the second condition of the linear operator. Now students, the second condition is that we know that the second condition is if we multiply with the constant with the function and the product of this constant and function multiply with the operator, which is equal to the constant outside of the bracket and operator multiply with the function. So we take left hand side, which is equal to the s into lambda f of x. So s is scaling operator, which is multiplied by lambda into f of x. According to the given condition, we take the square of this function, lambda into f of x का square into s. So which is equal to the lambda square f of x का square. This is equation 1. So the right hand side is equal to lambda s, no equal to left hand side equal to right hand side. So we take right hand side, lambda into s of f and lambda into s operator into f. So we take the square f of x square, which is not equal to the left hand side. So both equation 1 and 2 is not equal to each other. So left hand side is not equal to right hand side. So second condition is not satisfied. Hence scaling operator is non-linear operator. Simply students, आप लोगों को यहाँ पर ये स्केयर ऑपरेटर है और ये लैम्डा. हमारी कंडीशन है कि अगर हम किसी फंक्शन को उस कांस्टेंट से मल्टीप्लाई करें और देन उसका जो प्रोडक्ट है उसको हम ऑपरेटर्स के साथ ऑपरेट करें या ऑपरेटर से मल्टीप्लाई करें, तो आपके पास जो आंसर आएगा वो कांस्टेंट आउटसाइड ऑफ द ऑपरेटर होगा और ऑपरेटर जो है वो फंक्शन के साथ मल्टीप्लाई होगा. तो लेफ्ट हैंड साइड हम लेंगे तो लेफ्ट हैंड साइड हमारे पास जो है वो ऑपरेटर इंटू लैम्डा एफ ऑफ एक्स है. ऑपरेटर इंटू लैम्डा एफ ऑफ एक्स का जब हम स्केयर लेंगे तो आपके पास लैम्डा स्केयर इंटू एफ ऑफ एक्स का स्केयर आ जाएगा. इसको हम इक्वेशन 1 कह देते हैं. ये हमारे पास इक्वेशन राइट हैंड साइड के इक्वल नहीं आई. अब हम राइट हैंड साइड देखते हैं कि क्या वो इसके इक्वल आती है. अगर वो इसके इक्वल आ जाए देन वो लीनियर ऑपरेटर है. अगर नहीं आती तो फिर इसका मतलब है कि ये हमारे पास नॉन लीनियर ऑपरेटर है. राइट हैंड साइड इज इक्वल टू लैम्डा इंटू एस ऑफ एफ. सो वी टेक द स्केयर ऑफ द एफ ऑफ एक्स का स्केयर. दिस इज इक्वेशन 2. So equation 1 and equation 2 is not equal. So left hand side is not equal to right hand side. Second condition is not satisfied. हमने ये कहा था कि अगर कोई एक भी कंडीशन सेटिस्फाइड ना हो तो वो हमारे पास नॉन लीनियर ऑपरेटर होते हैं. तो अब यहाँ पर आप देखें कि हमारे पास दोनों कंडीशन ही सेटिस्फाइड नहीं है. इट्स मीन कि हमारे पास जो भी स्केलिंग ऑपरेटर होगा वो हमारे पास नॉन लीनियर ऑपरेटर होगा. Friends, so here is activity for you. You have 10 minutes to solve this example. The question is that a complex conjugate operator C is non-linear operator. To prove that C is a non-linear operator, take two conditions satisfied to both conditions of linear operator, first and second. Simply we take any function f and g with multiply C but the complex conjugate operator. Then we multiply constant with the operators. You know that change constant with the complex. So take the steric. So C constant when we multiply with the operator which is equal to the C star, the complex conjugate. So remember that and solve this example. Students, here is reference books. For further practice you can take more questions for your practice from these books and solve it. Now students, today lecture is end. Today we discuss about the linear, what is operator and the example of operators, how to represents the operators, and what is linear operators and non-linear operators, the difference between linear and non-linear operators, and related question and example we solved in this lecture. I hope so you understand all these terms. And Allah Hafiz. Take care.